In the past two videos, we built up the magnetic field H. We got it from Biot-Savart by integrating along currents, and more elegantly from Ampere's circuit law when the geometry was symmetric. But H is not the only magnetic field quantity we care about. There is a second one called B, the magnetic flux density, and today we connect the two. We will then write down all four of Maxwell's equations in their static form. The magnetic flux density B is defined by a very simple relationship. B equals mu times H. In free space, mu is the constant μ₀, which equals 4 pi times 10 to the minus 7. This number comes from the SI unit system. It sets the scale of magnetic effects the same way epsilon 0 sets the scale of electric effects. Inside a material, mu is generally different. We write it as μ₀ times μr, where μr is the relative permeability and captures how the material responds to the field. Why two field quantities H and B if they are proportional? Because H is what a current produces directly, and B is what acts on moving charges and causes the forces we observe. In vacuum, they're just scaled versions of each other, but in matter, they carry different physical information. The unit of B is Tesla, or equivalently, Webers per square meter. Now we define magnetic flux. The magnetic flux phi through a surface S is the surface integral of B dotted with ds. You can think of ds as a tiny patch of the surface with an arrow sticking out of it. B dot ds measures how much of B pokes through that patch. Add them up over the whole surface and you get phi, the total magnetic flux. The unit is the Weber, which is a Tesla times a square meter. This integral looks just like the electric flux from Gauss's law, and that's not a coincidence. The reason we define it is that magnetic flux through loops is what drives induction later on. Here comes the big difference between electric and magnetic fields. For the electric field, we had Gauss's law. The divergence of D equals the free charge density ρV. Charges are the sources of E. For magnetic fields, the analogous law reads divergence of B equals 0. 0. Everywhere. Always. What does that mean physically? It means there are no magnetic monopoles, no isolated north or south pole. If you take a bar magnet and cut it in half, you don't get a loose north pole and a loose south pole. You get two smaller magnets, each with both poles. The field lines of B always form closed loops. They never begin and never end. That's why the divergence is 0. At every point, as many lines enter as leave. In integral form, using the divergence theorem, this becomes the closed surface integral of B dotted with ds equals 0. No net flux out of any closed surface. Let's collect all four Maxwell's equations in their static form, the form that applies when nothing is changing with time. First, divergence of D equals ρV. Charges are the sources of the electric flux density. Second, divergence of B equals 0. No magnetic monopoles. Third, curl of E equals 0. The electrostatic field is conservative, which is why we could define a potential V. Fourth, curl of H equals J. Currents are the sources of the curl of the magnetic field. This is the differential form of Ampere's law from the last video. Notice something important. In the static case, the electric and magnetic fields decouple completely. The first and third equations only involve E and D. The second and fourth only involve H and B. They don't talk to each other. That changes when we let fields vary in time, but that's a story for another day. Quick wrap-up. B equals μh connects the two magnetic field quantities. The flux phi is the surface integral of B dotted with ds. Divergence of B is 0 because magnetic monopoles do not exist. And when we stack this next to the other three static laws, we get all four Maxwell equations for statics. This closes the block on magnetostatics, the last piece of static field theory. From here, two paths open up. Wave theory, where time-varying fields couple E and B together, and applied problem solving, where we use everything we've built to crack textbook problems step by step. That is where the course turns next.